Hi, my name is Anthony Willis, and this is Pennies Over Troubled Water. This is a science experiment that I conducted. So my hypothesis or question statement for this particular experiment is, what is the most number of pennies that a paper bridge can hold when the bridge supports are moved further apart? The outcome statement is, if the bridge supports are further apart, then the bridge itself should hold less pennies because there will be more weight in the center of the bridge that is unsupported. And the numerical number that I predicted during any given trial is that the bridge would hold only 100 pennies maximum. The way that this applies to science, or the science concept for this experiment, it is a physical science activity, and basically we're able to kind of see how different forces and weights, kind of how they work during this. Some of the key vocabulary, of course, is force and weight. So a force is the strength or energy as an attribute of physical action or movement. In this particular instance, we're talking about maybe compression or tension. So compression, they would push together, and tension, they would stretch apart. And we'll talk about that some little later. And then weight, of course, is a body's relative mass, or the quantity of matter contained by it, giving rise to a downward force, or basically, in a nutshell, it's the heaviness of a person or a thing. How does this concept apply? So this concept is important because it kind of allows students to understand the impacts that weight and force can have on a given object. Learning about this is going to help them consider different factors from this experiment, should they be required in the future to maybe construct something that is a little more sturdy or that supports more weights. So some of the variables in this experiment, of course, are manipulated variable, which is what we change. It's the distance of the bridge supports. So when I conduct this experiment, I decided I was going to move the bridge supports in 5 centimeter increments. So I start with 5, move to 10, and go to 15. Our responding variable is the number of pennies. So that's what we're measuring. We're measuring to see how many pennies that bridge is going to hold. And then, of course, our constants are the bridge itself, which is the paper, and then the height of the bridge supports, which are equal. So some of the materials here, we have, of course, pennies. We have a file folder, or if you have index cards, because those are already cut to the same size, those would work. I use 6 hardcover books as my bridge support, so 3 on each side. Of course, we needed a ruler. If you don't have index cards and you're using a file folder, you need scissors to cut those evenly, and then a pencil to record your data. So for the procedure, I'm gonna bring you over here so you can see it a little better. So here we have the materials. Again, you have your scissors, your sheets of paper that are roughly the same size. You have your bridge supports, your ruler, and you just need a little bit of common sense, some pennies. So the way you do this experiment is you are going to place your bridge on the supports. Now, I've already measured these for you, but if you start at the 0 on a standard ruler, and I did 10 centimeters, I know you can't see that there, but 10 centimeters apart. So then you have your bridge, and I found when conducting this experiment, it's more accurate when you stack them instead of just randomly placing them onto the card. At least that's what I found. So this is all you would do for this experiment. And you can see, as I'm placing the pennies here, underneath, that is where you have your tension. So if this were, let's say, an actual wooden bridge, you would have slats of wood underneath, and they would be stretching apart. And you can see that here with our bridge as well. And your compression force is going to be on the top because you have the bridge and it's starting to push together because you have so much weight in the middle. So if you think of it kind of like a balance beam, you know, if you are walking across, more weight is going to be in the middle, and you're going to feel that compression and tension at work. So let's see, we're up to 9, there's 10, and 11. So that is the experiment itself, and you can see that is how we got all of our data. And I conducted that trial 10 times at different increments with the bridge supports. So every time you do the experiment, just make sure you record your data, and then we'll figure out our average mean. So you can see here, I did trials for each of the different increments with the bridge supports. And overall, especially on trials 2 and 3, they were roughly the same. So the most I had at any given point for trial 2, 10 centimeters, was only 13 pennies. And you figure each penny weighs about 2.5 grams. The most weight that it supported was during the second trial of the first manipulated variable. And it held 124 pennies. But that is when I was placing them at random. So after that point, I decided to try and just stack them more evenly to kind of distribute that weight more equal. And I got more accurate readings, I think, by doing it that way instead of just tossing the pennies on there. Just some more of the data information. I think this can probably be better explained with a visual. So looking at our bar graph here, you see on the left we have the number of pennies. These are the bridge supports and their heights. And if you think back to the outcome statement that I made about the bridge supports being further apart, holding less, it proves accurate here. So at 15 centimeters, it held roughly an average of 7.5 pennies. When the bridge supports were only 5 centimeters apart, it held almost 90 pennies. So the hypothesis that I predicted was correct. Again, you can see here that the average number of pennies held at the shortest distance for the bridge supports held approximately 89, mid-range approximately 12, and then when they were furthest apart, the maximum number that it would hold was 8. So in conclusion, based on my hypothesis, I discovered that I was correct in my thinking about the distance of the bridge supports holding less pennies further apart as opposed to close together. The numerical prediction that I made, however, was incorrect. I predicted that it would hold only 100 pennies at any given moment, and during one trial it held 124. So I was close, but that's science. You're not always spot on. And I did again learn that when the pennies were stacked and more evenly distributed, it made a much bigger difference. Randomly placed, they could potentially hold more, but again, more evenly gets a more accurate result. So if I were to do this in the future, moving forward, I think instead of manipulating the bridge supports, I would try and manipulate the bridge itself. So I would kind of tweak the paper and try and support more of the weight that way. And there are some different techniques that students could try. But I think doing this experiment is important because this gives you kind of, it gives them kind of a foundational starting point. They can take what they've learned from this experiment and apply it to future experiments just like this. As far as the real world application, engineers, of course, would probably be your target audience for an experiment like this. And I have no doubt that they are conducting similar experiments just like this, but probably on a much larger scale. And it relates to the real world for students because most students have been on a bridge, they've seen a bridge, it's a safe bet that most kids know what a bridge is. And this experiment kind of helps them to see how a bridge works, I guess. And also just to apply it to science and engineering. It's a good opportunity to just kind of talk about engineering because that is science. It's designing and building. And you could also, I would also maybe open a discussion about what kind of factors in the real world might make a difference in the bridge, because there are different materials that engineers use, like steel or stone or wood, and those are going to have their own sets of strengths and weaknesses, and it depends on the design of the bridge itself. So they're all going to factor in, and I think that could be a good discussion either before or after an experiment like this. And as you can see, I did this all in one afternoon. It just took a couple hours from gathering the materials to finishing my third set of trials. And what's neat about something like this is if you pose a question and you want a scientific answer, it doesn't really take a whole lot of your time to look at it through a scientific lens and gather some of that information. And that's the experiment. Thank you for taking a walk on that bridge.